All right, let's dive right into this explainer. We are taking a pretty fascinating journey today to question the very foundations of the cosmos, specifically looking at the quest to fix gravity. For decades now, Albert Einstein's general relativity has been the undisputed heavyweight champion of the universe. But, some of the absolute most brilliant minds of the 20th century looked up at the cosmos and couldn't shake the feeling that Einstein's elegant equations were actually missing a crucial piece of the puzzle.
So, picture this. What if the fundamental rules of the universe were, literally, shifting right under our feet? We all learn in school that Newton's big G, the gravitational constant, is exactly that, a constant. It's supposed to be the unmoving bedrock of our physical laws. But what if it isn't? What if the actual strength of gravity is slowly fading away as the universe gets older? That is the explosive question that sparked a decades-long search for a totally new theory of gravity.
Section 1. The mystery of inertia. Tracing the cosmic puzzle back to everyday physics. Okay, to figure out why anyone would even dare to challenge Einstein, we really have to look at an everyday puzzle. Why do things have mass? Why does it take so much effort to push a heavy cart? And why does that same cart stubbornly want to keep moving once it's rolling? General relativity treats mass as a strictly localized property. But look at this quote right here from Austrian physicist Ernst Mach. Way back in 1883, he stated that we need an ideal insight from which accelerated and inertial motions result in the same way. Basically, Mach didn't buy that things inherently possessed inertia in a vacuum. He strongly suspected a grander, cosmic web was actually pulling the strings.
Einstein actually ended up calling this crucial idea Mach's principle. And it's wild. It suggests that your local reality is completely anchored to the distant stars. Think about it like this. If you spin a bucket of water, the water creeps up the sides. Newton said, well, that happens because it's spinning relative to absolute space. But Mach argued that the water is climbing the sides because it's spinning relative to the bulk of literally all the other matter in the universe. Your local physical forces are entirely generated by the entire cosmic background. It's an absolutely breathtaking idea.
Section 2. Dirac's giant numbers, moving from the massive scale of the universe to the microscopic world. So, while Mach had his eyes glued to the stars, other physicists were looking inward, right down into the space inside atoms. Enter Paul Dirac in the 1930s. As one of the founding fathers of quantum mechanics, he stumbles onto this totally bizarre mathematical coincidence. He calculates the ratio of the electromagnetic force to the gravitational force between a proton and an electron. Okay, fair enough. But then he calculates the ratio of the current age of the universe to the atomic unit of time. Two completely different realms, right? One dealing with the tiniest particles, the other dealing with the sheer vastness of cosmic time.
Well, the sheer mind-bending scale of what he found was 10 to the power of 40. Both of those massive ratios spit out a number right in the exact same ballpark, 10 to the 40th power. That's a 1 with 40 zeros. Dirac flat out refused to believe this was just a random coincidence. He proposed what's known as the large number hypothesis, suggesting that these incredibly massive numbers are actually causally connected by some hidden, fundamental law linking the macro and micro physical worlds together.
Section 3. The weakening of gravity. What happens when cosmic numbers grow?
Now, here's where things get really interesting. If the age of the universe is represented by this massive number and it perfectly equals the ratio of atomic forces to gravity, well, what happens as the universe gets older? As time ticks on, the age of the universe obviously increases. And since Dirac firmly believed atomic parameters couldn't change, the target fell squarely on gravity. Dirac's math led to a pretty stunning conclusion. G is proportional to 1 over T. The gravitational constant varies inversely with cosmic time. In plain English, gravity is fading away. When the universe was young, gravity was incredibly strong. Today, it's weaker, and tomorrow, it's going to be weaker still.
You can probably guess, this sets up a massive clash of titans. On one side, we have Einstein's standard general relativity, where G is an absolute constant, and matter and energy are strictly conserved. End of story. But on the other side, we have these alternative theories born from Dirac and Mach, where G changes with time. And, as a necessary mathematical consequence to balance out those equations, matter actually has to be continuously created.
And look, these alternative theories weren't just vague shower thoughts. They were rigorous mathematical frameworks. Notice our two heavyweight challengers here. First, we have Carl Brans and Robert Dicke, who in 1961 published a scalar-tensor theory, suggesting a hidden field actually dictates how gravity depends on surrounding matter.
Second, you have Fred Hoyle and Giant Narlikar, who developed a mathematical model that completely embraced Mach's idea of this deep cosmic interconnectedness.
Section 4. Continuous creation of matter. Balancing the cosmic scales. So, if gravity is slowly losing its grip, where exactly does that missing energy go? General relativity has very strict laws of conservation. To make these variable gravity theories actually work without completely breaking the universe, physicists needed continuous creation. Check out these two mind-bending proposals for how matter might just be conjured out of empty space. The first is additive creation, where matter literally just pops into existence uniformly across all of space, even in the deepest, emptiest intergalactic voids. The second is multiplicative creation, where new matter is spawned only where matter already exists, kind of growing in proportion to the atoms that are already hanging around. Hoyle and Narlikar actually took this a step further with their quasi-steady-state hypothesis. Instead of one single Big Bang, they proposed an eternal universe maintained by these mini-bangs. They theorized the existence of creation fields, or C fields, which continuously generate matter out of empty space right at the center of massive objects like quasars. The idea is that this local concentration of negative energy spawns new matter, which keeps the universe's mass density constant forever, even as it continues to expand.
Section 5. Testing the cosmic theories. Imagination meets hard data.
Now, these theories are wildly imaginative and mathematically beautiful for sure, but science is ultimately about observation. How do these variable gravity models actually hold up against cold, hard data? To figure that out, astronomers look for evidence of G actually changing, what physicists call G dot over G. Take a look at these measurement ranges on the table. Whether we're observing the moon's orbit, looking at distant supernovae, or studying ancient white dwarf stars, the results are pretty much exactly the same. The maximum possible change in G is virtually zero. The data strongly indicates that gravity just isn't fading. Ultimately, Einstein's general relativity remains incredibly, stubbornly robust. So what should you really take away from all this? Well, even though Mach's profound intuition and Dirac's brilliant numerical coincidences pushed us to question the very fabric of reality, the cosmos, at least so far, seems to side with Einstein. But the quest itself is absolutely vital. It forces us to ask, are the foundational rules of our reality truly permanent? I'll leave you with this provocative thought. If Einstein's constants ever do turn out to be variables in disguise, what else about our universe is just waiting to change? Thanks for exploring the cosmos with me today in this explainer. Keep questioning everything.